Okay, well, thanks for online audience and everybody coming to the seminar. And today's seminar, the only seminar is today and tomorrow. There's another seminar at the same time. We have our very own Stephen Theriault, who will talk about two problems in toric topology.
Right, so this talk stems from two problems that were posed, one by Martin in the graduate school and one by Taras as a question in one of the talks. And I don't know if I'm going to answer them in the way that they would like to have them answered, but I thought they were at least sort of topical. All right, so problem one. So this comes from Martin. And requires a little bit of setup. So if you sort of look at the construction of moment angle manifolds, and in a very particular case, so if you start with a polytope P square filled in, and then you let K be, take the dual of P and its boundary, and you get the boundary of the square. And there's the usual fibration from Davis and Yanuszkiewicz. So there's 4 copies of CP infinity involved, corresponding to the 4 vertices. I'll write the connecting map. You have some torus acting on ZK. And taking quotients in various ways, you get quasi-toric manifolds. So as Martin explained, 2 of these torus actions they're probably fibrations, but I'll say homotopy fibrations just to be safe. One of them gives you, you take 2 of the tori, let them act, and you get an S2 cross S2. So you quotient out to get an S2 cross S2, and you still got two tori left over. And you can take another quotient with 2 tori left over, but this time instead of S2 cross S2, you get something that looks like CP2, connect some CP2, and there might be an orientation reversal, but I'm going to sort of slosh over them. So the ZK in this case, you have a square, and it's not too hard to see that ZK is just going to be an S3 cross an S3. You want the square is the join of 2 copies of S0, and each S0 corresponds to an S3. So you have 2 tori mapping into a product of S3 and S3. So this is no homotopic. So is that one. And that means that after you loop, the loop of S2 cross the loop of S2 will be the same as these 2 tori. On that ZK. And the same for this guy. So this connected sum, when we loop it, you get exactly the same description. So there's this homotopy equivalence. And Martin's question was, what's going on, right? I mean, why is there a homotopy equivalence at this level? Well, we just did it. All right, so it's there. But for you loop, right? So S2 cross S2, if you compare it to CP2 connect some CP2, these are not homotopy loop. They don't even have the same cohomology. All right, so there's something that happens after looping to give you a homotopy equivalence. And in some sense, from the point of view of homotopy theory, it's because there's vibrations like this, and that's the answer. And that didn't satisfy Martin. And what I'm about to say sort of adds an extra wrinkle to things, but probably still won't satisfy Martin. So right. So these are, yeah. Right. Well, the Steenrod algebra acts differently, right? There's non-trivial Steenrod operations. Yeah. That's why I say there's no homotopy equivalence because yeah. Right. So what I want to do is produce a relationship between these two things. You can't get a homotopy equivalence, but a relationship between the two which exists before looping, right? So to do this, I have to bring in the cube lemma. All right, so suppose there is a homotopy commutative cube. So on the bottom, sorry, these are always time consuming to draw. All right, so suppose there's a homotopy commutative cube. Where the bottom face is a homotopy pushout. And normally you would say, suppose the four sides are homotopy pullbacks, but I want to add a little bit more. Suppose there's a map from D into some space Z where when you take the fiber of D into Z, homotopy fiber, you get H. If you map C into D into Z, take fibers, you get G. A into C into D into Z, take fibers, you get E. B into D into Z, you could take fibers, you get F. All right, so the square is formed by taking fibers of the bottom square all over Z. So the bottom face is a homotopy pushout, and the four sides are homotopy pullbacks. Obtained by taking fibers, say taking homotopy fibers over a map from D into Z. And the conclusion is that the top face is a homotopy pushout. So here's an example. Let's do the special case where the map B and C are the same space, and the map from A to B is just duplicated. So homotopy pushout. So pushout of a map over itself. And I'll call this then there's a nice push out map. Right? If you map B into itself by the identity in either direction, you get a push out map from D into B. And let's use that as this map from D into Z and take fibers everywhere. So we'll get a cube. Looks like this. All right. Fiber from D into B is some space F that we're trying to figure out. The fiber from B into B is just a point. Fiber from this B into B is just a point. And the fiber from A into B is some space G. Right? And the fact that this is a homotopy pushout along the top says that F must be the suspension of G. Right? So this is a homotopy fibration. So out of this, we get a homotopy fibration where we've identified the fiber from the map from D into B as the suspension of the fiber of the map from A into B. And this has a section, right? The map from B into D into B was the identity, right? So this will split after looping. Okay. And now we're going to wind back to the problem. Try not to erase too much. Right. So in our case, think of CP2 connect sum CP2. Well, any connected sum you can express as a pushout where CP2 you get from, you can think of, you start with an S2, take the Hopf map, and you cone it off to get CP2. Right? And anytime you have a connected sum, well, what is a connected sum? You take a manifold of dimension n, you cut out an n disk, you have another one of dimension n, you cut out an n disk, and then you glue them together along the n disks. And if you think about that, that's the same as taking the manifold with a disk cut out, the other manifold with a disk cut out, and then you glue them together along this common boundary. So that's that map from an Sn-1 into both. So it's really, you get a pushout when you glue together. And in this case, you would end up with a pushout from S3 to S2, another one from S3 to S2, and you get this pushout. All right, and that's exactly of this form. So we can apply this cube lemma thing, and we get a homotopy fibration where we start with CP2 connect sum CP2. We could map out to a copy of S2. This is a section after you loop. And the fiber is going to be, in this case, so the G in this case is the fiber of this hop map, and that's an S1. It's this push out map. So you could take the identity on S2 and the identity on S2 and get a push out map to S2. It's this bit. And we said the fiber of such a thing was the suspension of the fiber of this common map that you're taking the push out of. The fiber of that common map is S1. So its suspension is an S2. And the point is supposed to be that this matches the usual. So I'll put it in quotes here. This matches or corresponds to the usual fibration where you start with S2 cross S2, map to S2 by some projection, fiber S2, some inclusion. And of course, this has a section as well. All right, so this, my attempt at answering Martin's question is that there is a relationship between CP2, connect some CP2 and S2 cross S2 before you loop, in the sense that both fit as the total spaces in S2 fibrations over S2. Here, this goes back to, so you have this common situation, right? You've got a map from B into D into B, and that's the identity. Yeah. Whether Martin would regard that as an answer to his question, I doubt. But you can't adjoint this because there's no suspension. You mean this one? Yeah, so that would give you an S1 into loop on CP2, connect some CP2, and that would correspond to one of these. Yeah. And I didn't quite say, so the ZK in this case, right?
You could do the same thing. You could get a map and check that it's the same in homology.
Up here. I don't think they'd be this, well, the same, and I mean, these are different in cohomology.
Likely get a
Right.
map that's an isomorphism.
An isomorphism between, there's no way you could get an isomorphism in homology between these two, because
Additive.
additively, yeah.
You don't need a. You don't need a ring.
No, so additively, yes, they would have the same homology or cohomology, but not as rings. No. Mhm.
But it's also like another connected sound, like connected sound, the reverse orientation. That has different homology, and it's not. So over S2 there are two. So that your homology vibration is apparently not. There is no locally trivial vibration corresponding to that. Oh. Because if you over S2, there are precisely two fiber bundles with fibers. One is trivial and one is not. So this one is trivial, and the non-trivial one is when you take CP2 connects up with the reverse.
Yeah. So for that one you would. Yeah, I was thinking about that. There's a minus eta in here, right? And then the point is, when you try to when you try to map out to an S2, just putting a minus sign in here doesn't cancel out the minus sign here because they're kind of happening. You've
like
got a
opposites.
-1 on S3 and then a map which is not a co-H map, so it doesn't commute with this sort of a sign change. So that one you would get a little bit stuck with, yeah.
But there is still a vibration, right? So CP2 connects some CP2 is the reverse orientation onto S2. So that's the third kind of example in that line.
Yeah.
From the non-zero Toric vibration, Toric rises, there is some another one fan projects on the another fan, and then sometimes the fiber bundle. Yeah, that's the case. But this one is not a Toric variety. We do connect some CP2 is not a Toric variety, but we do connect some CP2 inverse.
Probably that is actually the inverse. I think that one might be the inverse because we use beta meters. Yeah, I might get one with the inverse actually. Maybe maybe it should actually.
So you would need a different argument, but you should get the same outcome.
Yeah, it interests me that this is apparently a homotopy vibration, which you cannot think of as a locally trivial fiber bundle, not that the top one.
Right.
You think that that's H-space structure of the loop space will play a role?
It's not equivalent to space.
No,
Just the space.
no, but
Right.
they are not equivalent as loop space. I think but as you could use the multiplication. You could still use the multiplication on that.
Well, in a sense, the multiplication is what's allowing you to multiply all these different factors together. Yeah.
This is what you said about that. There is no way if you put minus here, then there is no way you can compensate it with a minus in the other. But what does exactly this say? That other vibration doesn't have that there is no this fault map doesn't exist for the other vibration, but there is still it is still a vibration, even a fiber bundle.
Yeah.
Yes, you take what we're saying is if you take the Hawk map composed with the minus map on S2, you don't get minus the Hawk map.
Not necessarily, right. Yeah, I mean,
Right, so it's like.
Yeah, you have to sit down and think a bit more carefully about what happens there. I didn't do that. Okay. Right, so the second problem.
I think that's homotopy equivalence away from the Toric world. I think that
I mean, I should also mention there's nothing particularly new about this application of the cube lemma. I mean, it showed up in one of Lewis's papers. I'm sure it's been used many times before. It's just finding the right parts that go together to say something here.
Can you generalize that to arbitrary vibration over the moment angle manifold or arbitrary manifold? Same manifold, but they're making many things for that when
I think you could. This argument's quite limited because it needs this symmetry property, right? But there should be a better way to do this where you can sort of do what you're saying.
You're putting F on both horizontal and vertical.
Yes.
Yeah.
Yeah.
You say the attachment map. So the attachment map with the connected summary, just both block home. So you need the identity.
Yeah. So, I mean, I think not this particular application of cube lemma ideas, but maybe different applications could better answer your question. Okay. Mhm.
Well, clearly, the whole slew of Toric manifolds would need.
Yeah.
Well, but you need something that works every.
Right.
I wonder if there's enough of the same reason that they're all, whatever your Toric manifolds are, over the same.
Yeah, there's a lot of interesting questions here.
If it's independent, what Toric manifold is.
Yeah.
This depends on the Toric manifold.
Yes.
And the connected sum.
Yeah, maybe there's a better argument.
Well,
Can you iterate how fast to cross that?
Not in that way, because the connected sum, connect some 3 copies of CP2 together, you get something of dimension 4. Product thrift of 3s2s is dimension 6, but yeah.
Two
So,
times two.
Yeah.
Same.
That is all.
Three.
But probably what you're, I mean, but there are no board towers, right?
Yeah.
Right.
They're
Yeah.
kind of related by filtration on the cobalt.
Mhm.
Like the Toric and rational, the Toric things are formless, so. This with the cobalt, and they're kind of related by filtration. Like one is the same associated grade, different filtrations on the same.
Yeah.
Yeah, they algorithms are the same after filtration, they're kind of the same.
Right, okay. So problem 2.
Find out what group works in everything.
Yes.
That's the message.
Yeah.
For young people.
Maybe one last remark, connected some CP2 to blow up. Oh, this is not a blow up, the blow up, the other one blow up. How we do it, is the reverse. I think this one here, later I can get on the opposite. It's surprising.
Yeah. Okay.
Actually, the universal proof is that they're all equal to the same thing.
Right. So
That is why. No difficult now. But it's not coming from a fact. Yeah, it's not, yeah, sometimes even. It is a different, maybe you can get that much. Yeah, well, my question was, extend this number of product separations. Yeah, well, that's what I was.
I keep trying to understand that this homotopy vibration is probably not coming from a fiber bundle. That's somehow, yeah. It's just this fold map, and you take homotopy fiber. Yeah. You cannot make it into a fiber bundle, I presume.
that I don't know, but I'm yeah, I'm not concerned with fiber.
Yeah. 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 Right. That's what I don't quite understand, but anyway.
Right, so question 2. Yeah. I was trying to be provocative, get people thinking. Okay, so a little bit of setup. So this goes back to, let's see. Okay, so McGavran, before the invention of polyhedral products or moment angle manifolds or anything like that, showed that, phrased in today's language, if you take the boundary of an n-gon, where n is bigger than or equal to 5, and you look at the corresponding moment angle manifold, you get a connected sum of products of 2 spheres. And Sam Gittler and Santiago Lopez de Medrano generalized this So for example, if they would start with a cube, for example, you're thinking of it as a simple polytope, and you can cut off any number of vertices, look at the corresponding moment angle manifold, and that's a connected sum of a large number of products of two spheres. And there was a question running around as to whether you only ever get products of two spheres in such constructions. But then Chen, Ma, and Wong cohomologically and Erie diffeomorphically showed that there exists a simple polytope
It can't be your mic on. So.
It's always first one.
No, is it on, like switched on?
screen. Yep.
Well, there might not be a speaker here, but there might be people there. Okay, so should I ask?
Oh, can people online hear what's going on? I would,
Yes.
Steven says, yes, put a thumbs up or something, because I can't, there's no speaker in here. Just thumbs
Yes,
up if it's,
yes,
yes, I think they can hear what's going on.
Yes.
Otherwise, they wouldn't react to me. So-
yes,
But the thing is, the problem is there's no,
Yes.
there's, no, I think the problem is there's no speaker in here,
Yeah.
so we can't hear them.
yes. Okay.
Okay, thanks. We can't hear you because there's no speakers in here. Sorry.
Okay.
Okay. Yeah. There's no active speaker in here.
Yeah, so Chen, Ma, and Wong cohomologically and Erie actually geometrically showed there's a simple four-dimensional polytope with 18 facets that has the property that if you look at, we'll call this P, if you look at the corresponding moment angle manifold, it's diffeomorphic to S3 cross S3 cross S6. Connects some
Hello?
copies
Yes,
of
speaking.
S5 cross S7 connected
Oh, yes, hello.
together. Next some, sorry, 8 copies of that connected together.
Okay.
And 8 more copies of S6 cross S6 connected together. So this is the first example of a moment angle manifold where you had a product of 3 spheres showing up that connect some with some other guys.
Eight passes, but otherwise.
I had something here in my notes for that. What did I? Or maybe I got.
Mentioned an example, over on 1 page.
Okay, so ready? Right. Okay. So, as far as I know, that's the only known example. But it indicates that there ought to be more such examples, and possibly more with an even larger number of products of spheres. So, this was not exactly Terrace's question, but I think he was sort of angling in this direction. Maybe it was Steve Amelot's talk. And the question is, can you say anything about the loop space of this guy? Okay. All right, so like the first time, there's a question coming from toric topology, and to address it, we're going to forget about toric topology and just think about homotopy theory, right? So I'll start with a definition. Suppose there's a homotopy cofibration from A into X into Y. Then the map F is said to be inert if the loop on I has a right homotopy inverse. So what's going on is that you've got loop Y retracting off loop X, right? And it might be easier. Let me just, the example that you would normally think of would be something like a cell attachment, right? Where you've got an Sn minus 1 mapping to some X, and you're attaching an N cell. So when you do this, what normally happens, if this is just some random map F, what normally happens is you would kill off some of the homotopy groups of X, but then introduce new ones in the cofiber. All right. This inert condition says that because the cofiber, the loop retracts off the loop of X, when you look at, so the homotopy groups of this thing retract off the homotopy groups of this one. So F in this case will kill off homotopy groups, but it can't create any new ones. Right? And this is where the name inert is coming from. Right? This was studied by rational homotopy theorists in the 90s. There was a cottage industry of people looking at these inert attaching maps.
Before that.
And before that. Okay. But I'm not thinking rationally, I'm thinking integrally. Okay. So for example, if you look at something like a product of spheres, and you could look at the map that attaches the top cell to that. So you would attach that to some fat wedge. And I guess I'm going to assume this is N. So if you think about this cofibration, you're just attaching the top cell to this product. It's not too hard to see using Porter's theorem or whatever that the loop of this product retracts off the loop of the fat wedge, which by definition means that F is inert. Okay, so these things exist. And let's see. This is a higher weighted product. Yeah. Right. So I'll state a theorem. So recently, I was looking at these integral inert attaching maps. So this is posted this year, I think. In the following context. So there's this very nice theorem in rational homotopy theory, which says if you have a Poincare duality complex whose cohomology is not generated by a single element, then the attaching map for the top cell of that Poincare duality complex has this inert property. Right. So I was trying to show to what extent that held integrally, and came up with a criterion. So suppose let M be say an M-1 connected n-dimensional Poincare duality complex. And suppose, so when I say M-1 connected, I really mean that there are cells, there's non-trivial homology in dimension M, right? So the Hurewicz homomorphism would say you've got some map from SM into M, which is non-zero. And suppose that there's also a map out, which retracts that off. So this does not always happen, right? It's just a condition. So suppose there exists a picture like this, then the attaching map for the top cell of M has this inert property, right? So for example, this fits, right? Because if you look at the least dimensional sphere, you could always project it out. So you would get a section like that, okay? There's other examples. If you take some moment angle manifold, right, and think about a missing face of least dimension. So to let M sort of correspond to missing face of least dimension. Then the connectivity would say that you have an SM into a ZK coming from, you have a missing face, okay, of least dimension, which means you've got the boundary of a simplex, right? Look at the sphere that corresponds to that, map it in. You can also map it out using the Denham-Suciu trick of saying that you could project onto those vertices that correspond to the boundary of the simplex. It's the full subcomplex. So you would have something like that. So in a moment angle manifold, the attaching map for the top cell would be inert. All right, so there's lots of examples of these inert attaching maps. Okay, now, set ourselves up to use the cube lemma again. So suppose M satisfies this theorem. So for example, some product of spheres, and let N be any other n-dimensional Poincare duality complex. It doesn't have to have the same connectivity. It could even be just path connected. I don't think it even has to be simply connected. Then, let's see. So I'm thinking about connected sums again. So you have a push out. All right. M bar for the n-1 skeleton of M, and n bar for the n-1 skeleton of N. So you have a push out for this connected sum. That. And think about M. So M satisfies this nice property wherever it went. Here we go. I should have said here, I really want M less than N because I don't want M to just be a sphere. That's. So if M is less than N, the SM retracting off M means it will also retract off the n-1 skeleton. Right, so there's a map. Well, I could do it like this. I could look at that composite. This is 2 steps in a cofibration. So this composite's trivial. So I'm just going to put a trivial map in here. You get a push out map. And the fact that SM retracts off M bar means that it also retracts off this connected sum. So this is a substantial map. It's not just a trivial map. So apply the cube limit to this setup with this map as our map from the push out into a Z. So gosh. All right, so the fiber of this map is some space that we want to find things out about. The map from N bar into SM, that was trivial. So this fiber is just N bar cross loop SM. The map from Sn-1 to N bar to M connect sum N into SM, that's trivial because it's factoring through this trivial map. So this is also a product. And because they're factoring through the same null homotopy, they're compatible. So if I call this one, say G, and this guy F, this would be G cross 1. In this direction, the fiber from M bar into SM is some mysterious space G. And then I get some mysterious map theta from this product into G. Okay. So maybe a note or two. One is that, okay, so SM retracts off M bar, so it retracts off connected sum. So this is a fibration with a section. Um, right talk. Okay, a little bit more homotopy theory. Think about, well, we're taking fibrations vertically, right? So take the next step up, all right? This was all, the base in this case was all SM. So the next step up and looking at connecting maps, you've got loop SMs mapping down into G, F, this product and this product, right? In each case, that map's null homotopic. In this case, because SM is retracting off this connected sum, it's retracting off M bar, so the connecting map here is trivial. These are product fibrations, so the connecting maps are trivial. All of these are going to be compatible. So you can take this copy of loop SM and you can kind of collapse it out. Um,
Just the inclusion of that back. Connected homework is two back.
the connecting maps are trivial.
Map, there's a map from loop SM into both of those product things. And
Yeah.
it's just the inclusion into one factor. That's why you're pushing, that's what you're pushing about. Right?
Oh, yeah. So sorry. Yes, you're right. Yeah, sorry. Okay.
The other ones, it's trivial. That's why you
Yeah.
push it out there.
Right. Sorry. So let me, yeah. Scratch that. Thank you, Don. Yeah, I was muddling that up. The maps, the connecting maps into here are just the inclusions of these factors. But the fact that you have retractions means that they collapse out in the G and the F. Right. Thanks. Right. So that means, so there's a collapse of loop SM. Okay, I'm not going to say that. I'll just say theta factors as Sn minus 1 cross loop SM. And then collapse out that copy of loop SM. So take a half smash. And you get some induced map from that half smash into G. Okay. Now, if okay, good. My theorem is here. So I haven't told you how that's proved. One of the ingredients is that this map theta prime this has a left inverse. Right, so there's some work you have to do there. This is a non-trivial thing. That has a left inverse, and you actually get a homotopy equivalence between that half smash and some other space G prime. where G prime fits into G prime is the fiber of M into SM. All right, so this is sort of mysterious. It's an ingredient in the theorem. So what does this do for you? If you think about the push out at the top of that cube, right, then in both the map for theta and the other horizontal map, the loop SM is collapsing out, right? So there's actually a push out, a homotopy push out. That looks like that. G here splits as a wedge, where that map theta prime is just the inclusion of this factor. And that means, so this composite is just the inclusion. So when you push out, all you will get is a copy of this wedged with G prime.
To choose if there exists a theta prime such that that's the inclusion.
Yeah.
With the extension, there's many extensions that we have.
Yeah. All right, so the point is that you get to identify this homotopy fiber F, right? So you have a homotopy fibration coming from the vertical part of that cube, where you start with M connects some N, map down to SM, and the fiber is this thing. So I'll write it the other way around. So I'll write it G prime wedge N bar S smash loop S. Okay. So what? So now let's get back to the question. So in the question, we had some big connected sum involving a product of 3 spheres and lots of products of 2 spheres. So let's take M to be one of the copies of S5 cross S7, and we'll take N to be all the other stuff. So an S3 cross S3 cross S6 connected sum with 7 copies of S5 cross S7, connect sum together, connect sum 8 more copies of S6 cross S6 connected together. All right, so M connect sum N is the Chen, Ma, Wang, Irier manifold. All right, so we'll have a fibration where we have the Chen, Ma, Wang, Irier manifold mapping down to an S5, right? We need our G prime here right? That was the fiber of M mapping down to this sphere of least dimension. And that means that G prime is just an S7. There's an N bar here. That's easy to identify. N bar is going to be, remove the top cell. You've got a connected sum, so that means when you remove the top cell, you're just left with a wedge where you've removed the top cell of each of the ingredient bits. So you have a fat wedge on an on the S3 cross S3 cross S6 wedge with uh, 7 copies of S5 wedge edge 7, wedge with 8 copies of S6 wedge S6. And there's a homotopy vibration where you take M, connect sum N, map it down to this S5. Its fiber is G prime, so that's an S7. Wedged with the N bar. All right, so all of this stuff. Half smash a loop on SM. So M was the S5 here. And this vibration has a section. So it splits after looping. This you can, I somehow I feel like you can identify this because it's a fat wedge together with wedges of spheres, right? So if you want properties of this space, you could, in terms of the homotopy groups, you could look at properties of this space, right? You've got an S7 within N bar, you've got lots of spheres. So if you just picked one of the S5s, for example, you could retract off an S7 wedge S5, which would mean that this is a rationally hyperbolic space. It has infinitely many rational homotopy groups. It has no exponent in its homotopy groups at any prime. It has, for any, so it's mod P to the R hyperbolic. So if you look at the P to the R torsion in the homotopy groups of this space, it too has exponential growth. So you can read off all sorts of properties of this manifold because you've identified a fiber which splits off it after looping. And if you don't like this presentation, you could change it. You could say, well, instead of starting with my M being an S5 cross S7, let's start it with the S3 cross S3 cross S6. And then the N would be the connected sum of products of 2 spheres. All right. The G prime, so is there a different color? If I were to choose M, the S3 cross S3 cross S6, and the N to be connected sum of products of 2 spheres. This fiber, well, I'd have to pick the S3. And this fiber then would be an S3 cross an S6. The N bar would be a wedge of spheres. And you'd get a different vibration, right? Where now you'd be mapping out to an S3. This would look like you'd have a product of an S3 cross S6 together with wedged with this wedge of spheres. Half smash loop S3. So if for some reason you preferred to work with this sort of presentation of the homotopy groups, you could do that. So I don't know if this answers Terrace's question, but it was an attempt to say something about the homotopy groups of this Chen-Ma Wang Erie manifold. That's it. Thanks.